do here is we're going to look at both sections, 10.2 and 10.4. In 10.2, we learn really about heat. And then in 10.4, it's the modes of heat transfer. And we've already started talking about this in class a lot. We've talked about how air conditioners work. We've talked about how a refrigerator works. So we've really talked about a lot of this, but now we're going to classify it into some scientific terms that make sense. So let's start. First, we're going to define the term heat. Heat, again, is energy that's transferred because of a temperature difference. So when you take your hand and you touch the table, heat is flowing from your hand to the table. Whenever anything is colder than the other object, it flows from the hotter object to the colder object, always, okay? There's always a temperature change between hotter to colder. That's the direction of flow, always.
So I can give Liam.
Absolutely. Absolutely. Here's energy. There you go. So the concept here, the concept that we're thinking about is how can that heat transfer really? Not necessarily will there be heat transfer. If there's a temperature difference, there will be heat transfer. I'm telling you, if there's a temperature difference, there will be heat transfer. The question is really now, how does that heat transfer? Does it transfer through contact? Does it transfer like an air conditioner does through fluid flow? That's how an air conditioner works. Does it transfer the way a radiator works by radiating heat? So those are the three modes we're going to see today and discuss them. Okay? Let's take a look at this next slide first. We're going to talk in this next slide about the molecular behavior of a scenario where there's heat transfer involved. So you take a can of soda that says a can of juice. Juice is not in cans anymore. It's an old picture. You take it, not usually, unless like pineapple juice now that comes in a can. Orange juice is not a can anymore. Like apple juice. A lot of stuff is becoming cans. So imagine it's the summertime and you get a can of soda, or you go to the store with your parents, they're having a party and they get a bunch of soda cans and they put them in the cooler with ice. Now, the temperature of the can of soda might be, hypothetically in this case, 45 degrees Celsius. The temperature of the ice water is a little bit above freezing because it's ice water, it's not just ice, it's ice water. So it's 5 degrees Celsius. You drop the can in. The can is warmer than the ice. Therefore, from where to where? Yeah, can to ice, hot to cold. So the heat, take a look at the diagram here. The direction of heat transfer is in red. The heat transfer is out of the can into the ice water. Now, it has to travel from the fluid itself through the can walls into the ice water solution. So you have thermal, what are called barriers. Now, metal is not a good thermal barrier. It is a great thermal conductor. It's not a good thermal insulator. The reason we use this for cans is for that reason exactly. The actual can takes very little energy to cool it down because there's not a barrier. Now, if you take a thermos in the morning and you put hot coffee in it and you drink all day, it's still hot after like 4 or 5 hours. There's one of those fatigues. Inside of the thermos, there's an air gap. It's an air barrier. And in my engineering class this year, I had some students, one of the projects is called reverse engineering, where you have to kind of like take something apart and learn about how it works. So they wanted to learn how a thermos works. So they actually took a hacksaw and cut the thermos in half. And you can see there's like literally an air barrier in there. A window. These windows are single pane. So if you touch them, they'll feel cold in the winter. But if they were double paned, it's glass, air barrier, glass. And we're going to see that in the next 2 or 3 slides. I'm going to go back to that example with heat transfer. But the concept here is that the metal atoms are good conductors of heat transfer. So look at the molecules in green here. They're moving really fast. Why? Why are the molecules higher temperature, more kinetic energy. Now, the metal starts to slowly vibrate. The water is not moving fast at all because it's really kind of cold, right? Over time, what's going to happen to the can and the ice water?
Equilibrium.
They're going to reach, good, the two of you that didn't raise your hand, that's all right though. The two of you reach thermal equilibrium, yes. Thermal equilibrium, the same temperature. And that's this right here on the right. So the ice goes up to 11, the juice goes down to 11. The direction of heat transfer now, it's in equilibrium, so there is no direction. This is showing a balance. There is no heat transfer anymore once it's in equilibrium. But I want you to notice something. Why does the answer, right here, of where they meet, physically make sense? Why does the answer of where they meet, temperature-wise, physically make sense?
Isn't the average between the two numbers?
Is it? So 5 and 45, is that average to 11?
I don't know. No.
You could have said the word weighted average, I would be like, yes, Caroline, it's definitely a weighted average. Why is it a weighted average? What do I mean by weighted average?
I don't
It's
know.
multiplied by 1.4.
What's the weighted average?
What is a weighted average? A weighted average would be like 30 students get 100, one student gets a 90. The average is not 95, right? Average would be like a 99 or something. That's a weighted average based on the frequency of people that got the higher score.
Does it have to do because the can is smaller than the water?
Exactly. The mass of the water in a chamber or a cooler would be very large, right?
Yeah.
What's the mass of the can compared to that? Maybe like a 50th of it? Q equals, anybody remember chemistry?
Delta T.
What's the first
MC
one?
delta T.
MC delta T,
Oh,
right?
the
Oh,
heat
got
guy.
it.
The rapid, yeah. Anyways, it's totally that story. Q equals MC delta T, he's on fire, right? He's on fire. So, the idea here is that M for the can is much lower than M for the actual ice water. But Q is the same, because the heat that flowed out of the can, where did it go?
Into the water.
Into the water. So Q is the same, M is different, so delta T has to be different also. C happens to be different as well, but not significantly. It's the mass that is so much different. If the mass of one object is 20 times that of the other, it will only change temperature by 1/20th of what the other thing changes, if they have the same specific heat capacity, C. So
Sorry.
there you go.
So when the can is in ice, it's not the ice and it's cooling down the can, it's the can leaving out the hot.
The can is warming up the ice. The can is technically warming up the ice.
Yeah.
The ice isn't
That
really
was not
cooling
the
it
other
down.
way, just like cooling out was actually the hot.
The can is an exothermic action, and the ice would be endothermic.
Okay.
Okay? That's what you learn about those reactions in chemistry for this reason. Yeah.
So the masses are different, the temperatures have to be the same.
At the end, but the temperature change is what's different. Look, how much did the ice increase its temperature by? From 5 to 11.
6.
And then look at the juice from 45 to 11. 34 degrees. So the ice went up by 6. The juice went down by 34. The ratio of 34 to 6 is about 1 to 5, 1 to 6-ish. So that means there was probably 6 times as much ice as there was cans of soda. That makes sense? The mass of the ice was probably 6 times that of the can of juice because of the ratio of how much temperature change was there. Huge temperature change for the juice, not much for the ice at all. Okay? So what you would need to calculate, we're going to do this in the next section. So I'm going to show you how to do it, and then I'm going to run a lab tomorrow that I don't have you do as a class because it's one setup and we're just going to take data together, and I'm going to talk about how it works. But you would need the mass of both objects. You would need the specific heat capacity, C, of both objects. And that's it. And from that, you could, if you found the temperature change of one, you could find the temperature change of the other. So if you need, it would be one or the other of those two. Because Q is the same for both, so you're going to set them equal. Q equals M1 C1 delta T1 equals Q2, which equals M2 C2 delta T2. So you could set the Q equal for both. The amount of energy that the can loses is the same as the amount of energy that the water gains. As a result, the Q for both is the same. We're going to do more of this tomorrow with the math that I'm kind of just spitting out right now. Okay, but we'll see that tomorrow a lot more. Let's see. What else? All right, let's go. Units of heat. The first unit you know already. Okay? Yeah, joules. Energy, work are measured in joules. Heat is a form of energy, thus it's measured in joules. Now, joules happen to be a very small unit. So it's not necessarily useful to use joules for everything. It may not be useful to use them because they're such a small unit. So instead we use the term calorie. Now, calorie with a lowercase c is a different calorie than the calorie you're used to. The calorie you're used to is capital C calorie, or also known as kilocalorie. A kilocalorie is 1,000 calories. Well, a calorie is already 4 times that of a joule. So it's 4 times a joule, but then times 1,000, because it's a kilocalorie. And that is used for food. Where are the other forms? The original calorie is not really used much anymore at all, but older works in chemistry and physics use calories as their measurement of energy. The joule was used for a long time, and that's only used for SI units. The last one is the one that's also important, BTUs, British Thermal Units. Almost all devices now in the US are measured using BTUs. So an air conditioner has a certain amount of BTUs. A heating unit has a certain amount of BTUs. It's the amount of energy. It's another energy unit, British Thermal Unit. Okay, why do we use it in the US? Because we've adopted the English system of measurements. That's the reason. Just your units, understanding that there's different units. If I give you a conversion factor, being able to convert, if I tell you an air conditioner runs with 75 BTUs per hour, well, that's the amount of energy per hour. That's technically power in a sense. But if you have to use this number to convert to joules, so that you can then convert to figure out how much temperature change the room occurred. We're going to do the math part of it in the next section now. Okay, but recognize that there are different units that can be utilized and also changed. So if you have one unit, you could be able to change to the other.
Be given or will just be given out?
No, you don't have to memorize. I know, whatever that, right? So yeah, you'll be given a conversion factor if necessary anyway. So let's take a look at this next thing. Heat and work. Okay? You've heard the term do work before. That's when we talked about the charge carrier in a circuit. The charge carrier leaves the battery, goes into the light bulb uses the energy level of the charge carrier drops, there's no energy left. It goes back to the battery does work on the charge carrier, thus increasing the charge carrier's energy, and then it can go back to the circuit. So we've used the phrase do work before, and when you do work on a charge carrier, it increases the amount of energy. Well, it's the same thing. Go like this. What are you doing?
Doing work on energy.
You're doing work, you're applying a force over a certain distance. Work is force times distance. You're doing work, you're creating energy, you're creating heat. Okay, so when you do work on an object, you're really changing its internal energy level. Okay, its internal energy level. This is also analogous to exciting an electron. When you do work on an electron, it jumps up to an excited state. When the electron returns to its normal state, it emits photons, it emits light. That light can be picked up with a spectrum. I kind of cut out a section this year because we were running low on time, and in that section I talk about this concept, and you've learned about it in your chemistry class with the models of the atom. And one of the models of the atom, if you remember, the Bohr model of the atom, had to do with your spectrum for each element. That's where helium was discovered. Helios from the sun was discovered because it had a different electric spectrum that is provided. And every element has its own spectrum. How many of you signed up for forensic science?
Maybe.
A couple, maybe not. If you are, you're going to learn about this next year. You're going to learn about the fact that you could literally take any material and figure out exactly what it's made up of nowadays. It's incredible to think about. So if you had a piece of this desk, you could put it in a machine that can tell you the exact elements that are in this material.
That's cool.
Based on the electrical spectrum, the spectrum that is provided. So what I'm getting at here with the work is, if you do work on an object, it changes the energy level. That is what is used to determine what material is made up of. Changing the energy level, you look at the actual spectrum release when the electrons drop back down to their ground state. Anything else I want to add for this? A good example of this, obviously, you guys saw when you did this, but one that your book talks about. If you think about a nail, if you remove a nail from a piece of wood, you're overcoming the force of friction. Overcoming friction changes the energy level. The nail, when it comes out, you've ever done it, is hot. If you ever remove a nail from a piece of wood, you're going to physically be hot.
Like when you come out to touch the drill.
Yeah, absolutely. When if you're a science club group, when we were drilling that day, the drill bit on a drill when we're using it is extremely hot. Because what's happening is literally drilling away the wood. Friction. There's a lot of friction occurring. It's hot as anything. You touch it, you'll literally burn your hand right there. Okay, because you're doing work. Someone's hot as what? As you? If your heat is that high up, you have a fever, you should go down get it looked at, Nick. Wise guy. Keep going now. After that infrared joke you got me on. Infrared camera yesterday. I told the other class about that, Nick.
I didn't even know you believed that. I thought you were just going.
No, I definitely believed it. I really thought that was an infrared camera. I'm like, that's awesome. Were you not here yesterday? Nick took out his Snapchat filter that shows. Oh, sorry, photo booth, whatever. And it's a filter that looks like an infrared camera where you would see like the color spectrum of a body. It's like red and then blue, but it has nothing to do with the infrared rays. It's just like a filter of some sort that shows different colors. And he's like, oh yeah, I have the infrared camera because I was talking about it. And he's holding it up and I'm telling the class, oh look at this, you know. And he's like, it's not really infrared actually. I'm like, oh great. So, but an infrared camera, you can buy them. They're like $200 now. They attach right into the bottom of your iPhone or your iPad. It's FLIR, the brand, FLIR. If anybody has a lot of money they want to waste or they're looking for a birthday gift and they buy one, bring it in. It's pretty cool.
When's your birthday, Mr. Howie? Like giving
It's not so July. What are you gonna say? Why might this device be useful? An infrared camera. I think I've talked about this already. Didn't I? I talked about like pipes in a house. If your pipes freeze in the winter, you could literally, yeah, you want to see a person behind the wall. Yeah, the goggles that the military will wear, or a scope on like a rifle. It's infrared. Infrared seeks heat signatures. X-rays are totally different. X-rays have to do with the density of the material. It's a little bit different. All right, now we've talked about heat flowing and heat transfer. But what's important is that we get to these three topics here: conduction, convection, radiation. Start first with conduction. A prime example of conduction. I did this in the other class. Listen please. If I somehow had like a pair of tongs, tongs you would use on a grill, and somehow I could get them up to like 1,000 degrees. They're like white hot, not red hot, but white hot. And you attach the tongs to the end of this desk. You would see a heat signature radiating outward. Where this would be like red, then like yellow, then maybe like green, and then eventually over here it would still be cool and it would be blue. That would be a gradient or a contour of the heat signature. That's what you're seeing right here. So imagine heat is applied to the left side of the specimen. The left side heats up, and what happens? The molecules vibrate in a higher spot with a higher temperature, and eventually that heat propagates through the material. But at the far right of it, it's much colder because the heat didn't make it all the way there. The heat is lost along the way. The heat is dissipated into the environment. Okay, it is dissipated throughout. This is called conduction, when there's contact between two materials. So if you touch the stove and burn your hand, it's conduction. You're touching it, literally. If you ladies use a curling iron. If you accidentally touch yourself with a curling iron, conduction. Sure that hurts. If you take a pizza out of the oven, or anything out of the oven, you touch the rack with your wrist accidentally, and you get a burn mark there, I've had that several times. That's all conduction. It's all conduction. I'm going to finish, but let me take your questions first. No.
I was going to say, like when they're on the glass, and you lit up all the
it's radiation. We're going to get to that in the third one. That's radiation for sure. When we saw the different colors of the spectrum, that'd be radiation. Nick, what's up?
How do you get it to white hot?
How do you get it to white hot?
Don't tell them.
You use like most
Like it's red hot and hotter than white hot.
What do you mean?
White hot is probably.
The color of metal when it gets hot enough turns white.
So it's red hot.
Red hot is lower than white hot. Pretty sure. Pretty sure it turns like a clear, like a glowing white when it gets real hot.
I
That's why whenever you see
searched
like any
Whiteboard
sort
and
of
I got
like,
100.
whenever you see like any sort of
That's not what I wanted.
fantasy novel or stuff like that, like if there's ever like a sword, it's always like glowing white.
Ooh,
Right?
this
The
here.
idea of like high energy levels.
This.
Yeah. You've been doing work in the furnace.
I
A blacksmith.
Don't search white hot with flames.
What?
It's literally the opposite, but
It's different with flames, it's like a flame can be hotter than like a
Yeah, if you know stars, the temperature of a star is directly related to its color. Okay? And the sun is not the hottest of stars. The sun is yellow. So yellow is not like the hottest color. Okay? Anyhow, let me get back to this topic. Now, conduction, listen, involves contact. So when I touched this earlier, it was conduction. When you touch the window, it's conduction. So when you put a barrier, like a thermos, when you use a thermos to drink water from or cold or hot substance later in the day, or double pane glass windows, here's what it looks like. Here's the material, and what's in here? Air, or some sort of gas. And if it's hot here, let's say it's in the room, and this is the winter time, and it's cold out here in the winter, the heat wants to flow from the room outward. So here's what happens. The heat flow acts like this, and when it hits the air, it acts as a barrier. And we could demonstrate that with the diagram, maybe make the oscillations bigger to show that it's going much slower. And then it goes back through here and it goes much faster. So the air has what's called a lower conductive coefficient. Let's jot this term down. It's either a conductive coefficient or the coefficient of conductance, either one. Conduction coefficient. The conduction coefficient of a material is a material property. It's like density, or friction coefficient, or for fluids, viscosity, how viscous the fluid is. So it's a property of the material, the conduction coefficient. Gases in general have a very low conductive coefficient. The term, it's a K, the variable is K, by the way, like spring constant, doesn't matter. It's a conduction coefficient though. So since a gas has a very low conduction coefficient, it acts as a thermal insulator. Since that's gases like air or nitrogen or argon is usually between windows actually. Acts as a thermal insulator. Glass or metal, usually these materials act as a good thermal conductor. That's why you put Pyrex, right? Pyrex you use as a material a lot, or metal in the oven, like a cookie sheet is made of metal. It conducts heat evenly and well. So this is conduction. So remember, conduction involves what? What's the key word here? There you go. Contact. Key word here is contact. Let's go to number 2 we're going to see, and I'm going to show you a quick video of this, is convection. Convection uses fluid flow. Fluid flow. Okay? Movement of fluid. When an air conditioner cools down a room, it uses convection. The air flows from the top, it reaches the bottom, and pushes the hot air to the top, and it continues with this convective cycle. You see convective currents in the ocean. You see convective currents clearly, in this example of a tea kettle where there's water that's warming up. The hot water rises, eventually it starts to bubble, and you see that the actual water boils at the top. To see this as a physical example, I'm going to show you a quick video of this. And you can do this at home. It's not an extra credit opportunity just because I've given you so many lately. But you could try this on your own if you'd like to, if you don't either believe it or want to see it necessarily. So start with this one first. And I might speed it up a little bit. This person takes a food colored ice cube that's green. So it's an ice cube, you just put food coloring in it before you put it in the freezer. And what you're going to see, I'm going to fast forward, take a look. What do you notice? Where's all the cold fluid going?
Down.
To the bottom. And you can literally see this. It's an easy way to see convection.
No, it's like on one of those color tablets.
Yeah, that's exactly what it looks like. Now, let's see this now. This guy.
Well, there, back with another expression.
Okay, we don't need to talk. I can talk. So, what he's going to do is, he's going to take ice, and the ice is blue, it's frozen. Then he's going to take hot water and put red dye in the hot water. The container with hot water in it slowly permeates. So there's the blue ice, it's melting. Where is it going again? As you just saw at the bottom. The hot water, though, what do you think is going to happen? It'll be at the top. So eventually you're going to see that this really does separate over time. And you literally see hot and cold. Okay, it's kind of cool to show convection. Now, when will you see convective currents? You see convective currents when there's forced heat. So an air conditioner is forced convection. It's forcing cold air, which causes the hot air to do what? Rise up. Here it's not being forced. You would have to keep pumping hot water into this, or cold water, to cause the other water to start to flow like this.
Where do they say that in a fire you're supposed to lay on the floor too?
Why? And the smoke, both. One last video, go on. Okay. So, do you remember the soda can we put in the ice container a minute ago? Okay, think about the soda can, please, when you think about this. Is the door closed? It is, good. Just because it's black. So think about the soda can that was placed in the cooler. Okay, think about that. It's really corny, but...
See, even cold things have heat. Things like snow, icy mountain lakes, and glaciers. They've got heat. Anything with molecules has heat. It's just that the
So that's why we can't reach absolute zero. Think about that. Absolute zero would be the absence of heat. Besides needing the container to cool down further, it would be the absence of molecules altogether, really. Oops.
molecules in cold things are moving more slowly than the molecules in warm things. You with me?
It's really corny, but I get some of this.
Sing along.
Look at this guy.
Here's a question. Which has more heat energy? This hot burning match or this beautiful sculpture of science? Well, the match is hot, right? The sculpture's cold. Well, they're both made of molecules, right? But which has more molecules? The ice sculpture. A lot more molecules. So although they're much colder than the match, they actually have more heat energy. More molecules,
We did show
more
this
heat
earlier,
energy.
I know.
Think of it this way. Suppose you try to take a burning match and use it to melt the whole ice sculpture. Well, it's not going to happen, right? I mean, the match is going to run out of molecules long before the sculpture. So, more molecules, more heat energy. Ooh, ow, ow. Careful.
Such a funny show. Alright. So, the concept here I want you to remember is that the ice water had more mass, so it did not cool up or warm up as much, cooled down. Radiation is the third and final mode of heat transfer, one that occurs a lot. You radiate heat. The radiator literally uses convection, but it also radiates heat. A fire, at the end of a fire, where there's the coals, if you've ever gone camping, the next morning you wake up and there will still be coals. Coals stay all night. That's how, when you were back in the day, you would usually put fresh logs on top of the coals from the night before, and it would cause the fire to start up again. And every night you let the coals sit, so the next morning you put new wood on, and the fire would continue. So they radiate heat. It gives off heat. The sun radiates heat, but radiation is really traveling through like energy particles. It is not mass transfer. The other forms of heat involve mass transfer. Let's see what else. Objects in general that have more heat than their surrounding environment want to lower their energy, so they give off radiation. Please.